Section 3.9, more derivatives, this time exponentials and log functions. I'm going to put this quick review up. If you are not sure of your skills with logs and exponents, I would advise that you take a time to look through this quick review. Just pause, do the problems, and then once they're done, the screen with the answers will come up. I'm just going to kind of scroll through these a little bit at a time. If you want to do it, pause each screen so you can do the problems. If you're confident with your skills with logs and exponents, you can skip over this. So there's the first 6 problems. There's the last ones. And solutions. And solutions. If you have questions about any of those, let me know. So before we do this screen, and I should have put a blank on here, I apologize. Get your calculator out, and I want you to go to y sub 1. I'm just going to write here, I guess, because I forgot to put a blank screen in. Go to y sub 1, and I want you to put in the function 2 to the x. And then in y sub 2, I want you to put your end deriv, that's your math 9, and I want you to put d dx. And I want you to put in y sub 1 here, because we're going to change this y sub 1 several times. I don't want you to have to retype every time. So you're going to do y sub 1 using your vars. Whoops. Your vars, and then going to the right to y vars, choosing function, and choosing y sub 1. And then you're going to put your evaluated at x equals x. So do that and then hit graph, and you should get a graph of the two functions on top of each other. And you notice that they are very, very similar to each other. They're just a little bit different. Okay, once you've done that, come on back to your y sub 1 and change that to y equals 5 to the x. And tell me what you get now. So now we should again have something that looks similar, but not exactly the same. And I want you to do it one more time with y equals 10 to the x. So when you've done those 3 and you've looked at them, and you can see that their derivatives and the function values are really close to each other. So one last time, I want you to go to y equals 1 and put in e to the x, and then your y sub 2 is still your end deriv, d of d dx of y sub 1 evaluated at x equals x. That should not have changed. And now you should see that the graphs are exactly the same. In other words, if y equals e to the x, the derivative is also e to the x. So that's our first slide. The derivative of e to any function equals e to itself times, that's our chain rule. So if y equals e to the x, then y prime is also e to the x. If y equals e to the x squared, then y prime is e to the x squared times 2x. There's one more quick one, y equals e to the x cubed. So again, they've broken it down into that u substitution. So e to the u, du dx, and in this case du dx is 3x squared. They've resubstituted, and that's our derivative, or our y prime, of e to x cubed. So this function, y equals e to the x, is a very, very unique function in that it is its own derivative. Now, what if that isn't a base e, however? We already saw that if it's a different base, then they're close but not exactly the same. So if I want to find the derivative of something with a different base, like let's say base a, now I'm going to say that d dx of 3 to the u, or 3 to the x, we'll do it that way, equals 3 to the x times ln of 3. I've done it without a chain rule. I've just used an x, but I've used a different base. So our original one, e to the x, is just e to the x. d dx of 5 to the x is 5 to the x ln 5. Why isn't this then e to the x ln e? Well, it actually is, because ln e equals 1. So we don't write it, we don't bother with it, but it's actually all the same, whether that's an e or some other number. We take the exponential is its own derivative times ln of its base. And then if we add a chain rule, d dx of 7 to the x squared, we would get 7 to the x squared times ln 7 times 2x. That's my chain rule. Okay, so that's our exponentials. Pretty straightforward. Let's look at our ln. If u is a differentiable function of x and u is greater than 0, I cannot take the log of a number less than 0, then the derivative of ln u is 1 over u du dx. So again, our basic form, d dx of ln x, is simply 1 over x. Let's try one with a chain rule. Find dy dx if y equals ln of 3x squared. That's what we're going to have to do our chain rule on. So again, our function is ln of 3x squared. We're using u as 3x squared. So the derivative of ln is 1 over whatever this is times the derivative of the base, and that gets us this, and we can simplify this to 2 over x. So ln's and exponentials, pretty simple. If the base is not ln, again, we've got to deal with that ln a. This time it goes in the denominator. So again, looking at a simple one with a different base, d dx log base 3 of x would be 1 over x times ln 3 all in the base. If we do one with a chain rule, d dx log base 5 of x to the 4th, 1 over x to the 4th ln 5 times 4x cubed. 4x cubed over x to the 4th ln 5 will give me 4 over x ln 5 in the denominator. Okay? Couple other rules that we're not going to use quite as often, but we're going to go through them. Well, actually, this one is just another generic rule for powers. If this is anything, whether it be just a number or something else, we are going to always use that power rule, bring the n down, n minus 1, and then du dx if that is something other than a simple variable. So for example, we're just adding our chain rule to the rules that we've done before. So dy dx, we're going to start with our power rule, bringing that down. So using the power rule, the cube root of 4, 5x, the base stays the same, and it's the cube root of 4 minus 1, reducing the power by 1, times, using our chain rule on this, times 5. And that's it. We can't simplify it any further. So we've just added to our power rule by adding a chain rule to our base. The last topic here is logarithmic differentiation. Whoops, sorry, they just cleaned that up a little bit by multiplying the front by 5. Okay, sometimes the properties of logarithms can be used to simplify the differentiation process, even if the logarithms themselves must be introduced as a step. The process of introducing logs before differentiating is called logarithmic differentiation. One of the nice rules that we have about ln, if we have ln of x cubed Remember, our power rule allows us to bring that power down to the front. We are going to use this when we have a variable in the base and the power, because that allows us to take a variable that's up here that's very difficult to differentiate and bring it down in the front to use a simple product rule. So let's take a look. So I've got a variable in the base and a variable in the power. So I'm going to introduce logs to differentiate. So there's our original function. By taking ln of both sides, we've introduced our log. Now, we are going to have to use implicit differentiation as well here. The reason for using the log was that we could bring that cos down to the front. So we've used the property of logs to get that cos down in front. Now I'm going to take the derivative of both sides. I've got to differentiate this side implicitly because it's a ddx of y. We have done this before. And I'm going to use this side with the product rule. So the derivative of ln y is 1 over y dy dx. That's our implicit. I like to write it 1 over y prime. On the right side, the derivative of the first times the second plus the first times the derivative of the second using our ln rule. So that's our product rule and our ln rule all combined. Now, the next thing I want to do is solve for dy dx. So I'm going to multiply both sides by y. And then in order to get this back in terms of x, I'm going to substitute. Remember at the very beginning we knew that y equaled x cos x, so I can put that in right here. Substituting back in, this is my derivative. Okay, there's a lot going on here. We've got adding our logs, bringing this down in front, implicit differentiation on the left, product rule on the right, and solving for our dy dx or our y prime, whichever way you write it. I don't know why that's an s, that should be a d. Okay, so that's it. A bunch of rules and some combining of all of the different things we've learned together. We'll be working on this in class.